in two situations. One is, of course, we have quadrupole nuclei, and if you have a non-zero EFG, then that has an effect, because how the energy levels are shifted, that impacts and so on. The other is even without the quadrupole, the hyperfine coupling tensor might be anisotropic, or the susceptibility might be, or both. So that also has an effect on the line shape. So just the notation and how all this evolves, that's what we'll look at. So in presence of a quadrupole moment and an EFG, how are things modified? So if you want to look at energy of, if you have a charge density, okay, and it is subject to a potential, external potential, right? So, right, you have some charge density, maybe some R dependence. In our case, there will be no R dependence, but okay, there's some charge density, and it's subject to a potential is because of what the neighboring ions are. So, how do we write this energy? It's basic electromagnetism. I mean, you'll recognize it as a combination of a monopole, dipole, quadrupole, and so on. But general, it just
balance potential.
That's it. Over all space, there is no. Okay. So I mean, just classical. And then what we do is we basically take the nucleus to be point-like. Okay. And then it's finally true. Nucleus is point-like, and then you have charges around it which are generating some potential, and so you can expand this potential in a Taylor series around R equal to 0. Okay, so that's where you will get the potential at 0 one term, then del V del R at R equal to 0 another term, then second derivative, third derivative, and so on. Right? So the higher order term. So if you do a Taylor series expansion of the potential around R equal to 0, you can write it as VR is V0 plus, so when you have various components, X alpha del V del X alpha at R equal to 0 plus second derivative term, so 1 over 2 factorial, and you have X alpha, X beta, and then del square V del X alpha, del X beta evaluated at again R equal to 0, and then higher order terms. Right, this is standard. Always general convention is that repeated indices means you have to sum. So it's X, so if you are thinking Cartesian coordinate, then x1 del V del x1 plus x2 del V del x2 plus x3 del V del x3, and likewise here we get different kinds of combinations. Right, so one can use this kind of expansion for V of R, put it back in here, and then you just see what the various terms are. Okay, so your x1, x2, x3 are just the x, y, z. So you'll have a monopole term, right? You have the first term as B0, and so that comes out, and then you have just rho r d tau integrated, so that's the total charge. So this is going to be like atomic number times electronic charge, same as proton charge, V0. Okay. So I mean, this is some overall shift. This is always there. It's just some overall shift of the energy, right? So there is no orientation dependence, there is no magnetic field dependence, nothing. So we can just ignore it. It's not going to contribute to anything. Okay. Whether there is a quadrupole or not, this will always be there. So we can leave it out of all our calculations. You just want to know how the energy changes because of this. So all this doesn't contribute. Then you have a dipole term, right? So that looks like so E energy of the dipole term. Of course, you have a component of the derivative of the potential, right? So del V by del x1 or del V by del x2, and integral rho x alpha beta. This V alpha is del V del x1 evaluated at r equal to 0. So that's, you pull it out of the integral. What remains inside, this is the dipole moment basically. Right? And as it turns out, experimentally also for nuclei, so this is the nuclear dipole moment, this is the position, so this is the nuclear charge density, etc. So no nuclear dipole moments have been found. And also one shows that if there is a definite parity associated with the wave function for this nucleus, then one can show that the dipole moment becomes 0. So once again, the monopole term we can ignore. There is no dipole moment in practice, and also one shows that if there's a parity associated with the wave function, which it is, this also doesn't contribute. So the first term that contributes is the next one, the x alpha, x beta, integral, whatever. So yeah, so E quadrupole is then half V alpha beta. This is del square V del x alpha del x beta evaluated at r equal to 0. So half V alpha beta, and then integral charge density, and you have x alpha x beta beta. Okay, this is the classical picture, that if you have some charge density and is subject to some potential because of neighboring charges, then in increasing, in decreasing order, sorry, in an expansion you have a monopole term, dipole term, quadrupole term, octupole, higher order term. Okay, we realize that the first two don't contribute. This is the first one that contributes, the quadrupole, so we deal with this. Okay. Charge density for nuclei, we'll assume they're basically Dirac delta functions. You have point-like charges. And further, you need to write the quantum mechanical equivalent. So h cube, okay, maybe curly h, m prime. You have nuclei of I angular momentum, and you have states m sub I, and then various elements of this additional term m prime of the quadrupole part will be given by just half V alpha beta, and the quantum mechanical thing you'll write expectation value. So sigma over various charges that are there inside. So nominally you'll write EI, but it's really the same charge. It's E is charge on electron, but also charge on the proton. That is what is relevant here. We're talking about nuclear charge density. So then xi alpha, xi beta, and then we intentionally, not 1/2, 1/3, we add one term by hand, which is actually otherwise 0. Okay, it actually was just xi alpha, xi beta, and then psi m star on one side, psi m prime on the other side. This has some transformation properties, so we have added by hand 1/3 Dirac delta alpha beta Ri square. Okay. So again, one can show that this last term actually makes no contribution. It's actually 0. So which is related to the fact that your doing del square V, your charges, fixed charges are from other ions which are somewhere, and you're looking at the nucleus. So what is del square V? This potential is because of all the other charges. So what is value of del square V? 0. There's no charge here, right? So rho is what it is. So this is 0. So in our notation you have Vxx plus Vyy plus Vzz equal to 0. Okay, it's because of this that this integral finally, which involves Ri square and then V alpha beta, and there's anyway delta alpha beta, so it's only the alpha equal to beta terms which contribute, and you'll have 3 such. So this will therefore make that term go to 0. Okay, so the reason for adding this is one uses then, I don't show the details, Wigner-Eckart theorem to convert this coordinate tensor to angular momentum operators, and through which are related through this constant. So so next step is writing this same Hamiltonian, but instead of these coordinate related operators, we convert them to Ix, Iy type of operators, and through some constant. Okay, so because these wave functions, this various states of this nucleus with angular momentum I. So you know how to act I plus or Ix, Iy on these states. So we then know how to evaluate those integrals. Okay, so again, I don't work out the full details, but that integral is then some constant which is known from atomic molecular physics, times, again, same integral, psi m star, and inside you now have I alpha, I beta, plus I beta, I alpha, minus 2/3 delta alpha beta I square and psi m prime, or d, whatever spin space you might integrate. So the xi alpha, xi beta, and then the 1/3 delta alpha beta r square. So that is converted to, instead of x alpha x beta, it's converted to I alpha I beta. Instead of the r square, you have I square. And this constant takes care of the conversion. The constant is obtained by setting alpha equal to beta equal to 3. And you have the value of the constant. Again, I show it, I write it without proof here. 3 by 2i times 2i minus 1 and integral psi star sum over I of ei zi square minus 1/3 ri square, and then psi I and d tau. I runs actually from 1 to
the capital psi star.
yeah.
Is this the IZ value?
Yes. So this is for specific case. You're right. Yeah. This is for m equal to m prime equal to 3. Yes. And so the maximum value is I. M sub I is equal to I. And it's for that specific case. And alpha equal to beta equal to 3. We pick these two cases, and then this is equal to I, and then this is known from Clebsch-Gordon coefficients corresponding to transformation of coordinate operator to the angular momentum operator. Okay, so this is one thing. So you have converted the Hamiltonian from starting from classical ideas, the multipole expansion. So what is the energy because of the quadrupole moment? And that you have converted to something involving spin operators. Now in again standard notation, so this quadrupole moment is defined as small e times capital Q. Okay, that's the notation. This is just the electronic charge or the proton charge, and this is so whatever is in here. Not right. So this integral is what is the quadrupole moment, E times, it's written as EQ. Okay. Classical EQ is integral rho of r and 3z square minus r square d tau in the volume. So that's the classical quadrupole moment EQ. And our quantum mechanical quadrupole moment is just similar thing, except now you have expectation value corresponding to these wave functions. Okay, so I've sort of absorbed a lot of steps in going from one to the other, but finally the quadrupole Hamiltonian with this background information looks like. HQ is now EQ by 4I times 2I minus 1 B alpha beta and then I alpha I beta plus I beta I alpha. Okay, so this is the quadrupole Hamiltonian. Remember, our intention is in a usual Zeeman effect in the presence of a DC field, you get resonance, so you have energy levels equally separated, right? If you have m equal to whatever, half or 1 or 3 half, 5 half, whatever, adjacent levels, whatever is the energy difference, they're all equally separated because that's how the eigenvalues are. We want to now understand what happens if you have this term also in the Hamiltonian. Maybe first without the Zeeman, just this one, what will it do? And then with the Zeeman and this other weak perturbation, then what will it do? So these are the things we want to understand. So for that purpose, we want to know what the quadrupole term in the Hamiltonian. It is this. So couple of points to note. So you basically have the EFG tensor now. Okay, you have various, it's a 3 by 3 matrix. So because you have alpha, beta, alpha runs from 1 to 3, beta runs from 1 to 3. Right, so you have various terms, in principle, V1, 2, V2, 2, V2, 3, and so on. Okay, so remember, it's a traceless tensor. The diagonal terms are Vxx, Vyy, Vzz. So sum of that is what is del square V. That is 0. Okay, it's a second rank symmetric traceless tensor. V1, 2 and V2, 1 are going to be the same. Okay. Now again, couple of other notation things. E small q is defined as the second derivative, electric field gradient. This component Vzz, whatever is the highest, that by definition is, so forget the Zeeman term. Let's say you have only the quadrupole term, and you pick the principal axis. So it's only Vxx, Vyy, Vzz which are going to be non-zero. Pick the z-axis to be the one along which you get the maximum EFG. Okay, that's by definition the z-axis. for the EFG tensor, and then this is the VZZ is called EQ. We'll use that in finally writing the energy levels. And another thing we define is this parameter eta, which is asymmetry. So Vxx minus Vyy by Vzz. So EQ, small q, is the z component of the EFG, and eta is the asymmetry parameter. Okay? And principal axes we choose such that Vzz is greater than or equal to, next is Vyy greater than or equal to Vxx. Okay? So if you choose it like that, then eta varies between 0 and 1. Okay, so of course eta equal to 0 means there's no asymmetry, Vxx equal to Vyy, and eta equal to 1 means Vxx equal to 0. Okay, right, so the sum has to be 0, right? So Vxx plus Vyy plus Vzz is equal to 0, and if you have no asymmetry, then Vxx equal to Vyy. If you have like full asymmetry, eta equal to 1, then Vxx equal to 0, and then therefore they need to have opposite signs, right? Vyy must be minus Vzz, that will give you eta equal to 1. Okay, so in this situation, HQ is E square QQ. You know, we have compacted things now, divided by 4I times 2I minus 1, and then you have 3IZ square minus I square plus eta times Ix square minus Iy square.
So this symmetry has nothing to do with the symmetry of the satellite axis. This is different symmetry we are talking about.
What do you mean symmetry of the satellite peaks?
I mean, ideally satellite should be symmetric over the central peak.
So we have to find out what the position of the satellite.
I mean, just visually, if we see that दोनों symmetric नहीं है, so that is nothing to do with the expression.
Not really. The shape we have to see what happens. Suppose you have zero asymmetry or some between 0 and 1, then you know what. So you have to find out basically for various transitions now, what are the, how does the energy levels move? That's what. So we'll do one by one, right? So yeah, so this is the pure quadrupole Hamiltonian. So what we have done, if you realize, that we had we had a in the full Hamiltonian, we had a half V alpha beta, okay, and then this one through a constant was converted to something containing I alpha, I beta alpha, etc. Okay, so there's a half V alpha beta. So the constant was here like this, so the half will make a 1/4 now, okay, and then this is just the constant, you have to still put the V alpha beta, and also so this is what the Hamiltonian is. You have this half is from here, so and then you have to so half V alpha beta, the half is included as a part of this. And then this is from the definition of quadrupole moment. And then the VZZ, you know, when alpha equal to beta equal to 3, that is called EQ. So you're combining all that, and you have all these, your repeated indices you have to sum. So you'll have alpha equal to x, beta equal to x, alpha equal to y, and then accordingly you'll have terms in the brackets also. You have to sum all those. That's the total Hamiltonian. So there you'll get. So you had a 1/3. Anyway, you have to work with a small algebra. You get this. So the VZZ gives you a EQ. The quadrupole part gives you another E times capital Q, and so therefore you have a E square QQ here, and this continues. And inside you have to just sum the various terms, and you get something like this. Okay. Okay. Now, first we'll do both Zeeman plus weak quadrupole. Okay, then we'll see what pure quadrupole will give and so on. Yeah, by the way, you can already see, suppose you have to do energy levels for a pure quadrupole. So let's say we have spin 3/2. So m sub I is of course 3/2 minus half minus 3. Okay. You can see from here. So what you have to do is you have to find out the matrix elements of this. How does the energy level change if this is a small perturbation? First order perturbation theory.
Expectation of the perturbation with the ground.
With the same state, HQ in the middle, correct? So you will find from there the way these are operating, whether it's plus 3/2 or minus 3/2, energy is the same. So, but plus half or minus half, the energy will change because the way these apply on the states. So minus 3/2 Hamiltonian minus 3/2 will be same as 3/2 Hamiltonian 3/2. Okay, so plus minus 3/2 will be still degenerate, but different from plus minus half. So if you had a pure quadrupole, no Zeeman, then this degeneracy is partly lifted. You have only two levels now, and that's the transition, pure quadrupole transition, that's the one you can have. With the RF field, then you can excite and then create population inversion, etc., whatever you like. Okay. Now, if you have both, in real case, we are often doing in a magnetic field, and your nucleus has a quadrupole moment, and in the local environment of the crystal, there is a electric field gradient. So both Hz and HQ both are present, right? So you would want to consider the situation where the Hamiltonian is Zeeman plus quadrupole. So for this purpose, what we will do is, so some slight change of notation. So minus gamma h bar field, DC field, times Iz, minus mu dot h. That's what you're writing here. Now we have chosen the z-axis is the direction of the applied field. So in the quadrupole Hamiltonian now you will write some primed axis, because those, and the way it is written, those correspond to the principal axis of the EFG tensor. Okay, so you write the same HQ, but I'm just not writing it full. You'll write in rather X prime, Y prime, Z prime. Okay, which in general can be different from.
So like this could be some sort of local crystalline axis.
Exactly. Yeah. Local. So wherever the whichever direction the EFG is maximum, that is my Z prime.
So won't there also be some sort of anisotropy energy, like some correction due to the anisotropy that we should include? Because they are not the same.
These two are not the same.
The axes are different.
These, I mean, the applied field or choice for the.
Right.
Right now, I mean, first thing you consider is this is much weaker than. This is much less than the Zeeman. So those states that you get, I, mi, those are still valid. Yeah. So now, if they're comparable, then I don't think there's an analytical solution, because which are the states now, eigenstates? You can't. Only when there's a perturbation you can find out the matrix element, change in energy and like this, because these are still valid states. But if this condition is no more valid, then this is also not, you cannot apply perturbation theory. So then actually it's not amenable to exact calculation. The two extremes one can do, pure quadrupole, pure Zeeman, and then a small quadrupole on Zeeman, or maybe the other way. Okay, so you would write this, and we want to now see how the energies change. When you add a quadrupole term to the Hamiltonian. Okay, Zeeman case, you have minus 3 half, half, minus 3 half, and spacing is same, h nu naught. Okay, spacing is same. So now we again define nu q. This will be the quadrupole frequency. We define nu q as 3 e square q, small q, capital Q, by 2I times 2I minus 1, and then there's a Planck's constant below. Okay, because otherwise h nu is a dimensions of energy. Okay. And also nu naught is your usual precession frequency, so gamma by h naught, right? So usual Zeeman effect, you have a field and then you have precession of the nucleus about the applied field, and that precession frequency is nu naught. So with this notation, the Hamiltonian now looks like minus h nu naught Iz, right? And the quadrupole part looks like h nu q by 6, okay? And then inside you have 3I z prime square minus I square plus eta times I x prime square minus I y prime square. Now, remember now your z-axis is the axis of the applied field, and these are in general different. So you have xyz coordinate or orthogonal coordinate, and you have x prime, y prime, z prime. So, common origin, the other is z prime is rotated with respect to z by some angle. So you take theta, the Euler angle, theta, psi and phi, corresponding to the rotated ix prime, iy prime, iz prime. So we'll take phi equal to 0 without loss of generality. You can argue that. And then theta is, you have z-axis, so the z prime, y prime, x prime is rotated. So z prime is, what is the angle? Z prime is rotated by angle theta with respect to the z. And then within the plane also, you will rotate x prime with x, y prime with y, that's the other angle, psi. And you're not doing a third rotation, it's not needed. Okay. So anywhere along this theta, you get the same answer. Okay. So then what you have to do is, right, so you have to actually operate these on your states. So you need to write down ix prime, iy prime, iz prime in terms of the ix, iy, iz. Okay, but that is rotated, so you have them. Again, I just write the answer here. Ix prime is ix cosine psi plus iy cos theta sin psi plus iz sin theta sin psi, and likewise you'll write iy prime as minus ix sin psi, and then the others will have a cosine plus iy cosine theta cosine psi plus iz sine theta cos yeah. Okay, and then there is this iz prime also. Right, so we have also iz prime. It is just minus iy cos theta plus sine theta plus ix cos theta. Okay, and then again for these angular momentum operators, m I alpha I beta m is equal to 0 for alpha not equal to beta. Also m ix square m same as iy square, and this is equal to half m I square minus iz square. So job is in principle straightforward. You have the Hamiltonian ix prime, iy prime, iz prime. You need to rewrite in terms of ix, iy, iz, and then calculate the matrix elements for the what is the energy change? It is m quadrupole Hamiltonian m. This is what you want to find out. How? So for m equal to 3/2, initial energy was just based on Zeeman. Now, in the addition of a quadrupole, what is the correction? Similarly, for m equal to half, what is the correction? M equal to, I'm talking about spin 3/2. M equal to minus half, what is the correction? M equal to minus 3/2, what is the correction? Right? So we want a general expression for something like this. So one has to work the algebra, and the result is as follows. So again, first order, energy change in first order. So this matrix element HQ between m and m looks like this. You get h nu q by 12. You get 3m square minus I times I plus 1. And then, of course, you will get angular terms, right? So you get a 3 cosine square theta minus 1, and then there is a eta asymmetry parameter cosine 2 psi, and this multiplies cos square theta minus 1. Looks reasonably involved, right? So these are going to be the energy changes to the Zeeman levels, right? So what is the Zeeman case? Something like this, right? So remember what the Zeeman term in the Hamiltonian is? Minus, sorry, okay, no need to write. Minus h u naught is iz, right? So you're going to have 3/2, half, minus half, minus 3/2, but these are identical, adjacent levels. So in the shape of the resonance line, you're just going to get a single line, right? Only one energy. If you now add a quadrupole part, so it depends now on the angle. This theta is the angle that the azimuth, but I mean the z, the maximum of the EFG, whatever the principal axis makes with our applied field, right? That's the definition. Z prime with z. That's what is theta. And likewise, you define psi and phi. So, first point. So this depends as m square. Okay, so there's going to be a change in energy of each level compared to the zero, because you have all this. It's not going to be zero. But whether m equal to plus half or minus half, for a given angle, it's going to be the same change. Right? So similarly, plus half or minus half, it's going to be the same thing. Let's now, just for simplicity, let's take, this unnecessarily complicates, we'll see what that is. Let's take eta equal to 0. And also calculate for cos theta equal to 1. So theta equal to 0. Right? So they are aligned. My sort of crystal axis, often the EFG is along the crystal axis, so doesn't matter. So z prime is z. Okay. So calculate what are the various new levels. Okay. This is the additional term, right? So just go ahead and calculate. For this case, what is for m equal to 3 half minus 3 half? How does it change now? So now I have to say whether this goes up and what happens now. So just work out. So you put m equal to half, m equal to 3 half, m equal to minus half, m equal to minus 3 half, and cos theta is 1, theta is 0. Just calculate what is this matrix element.
It is 8,000 q by 2.
Correct? And the other one? Right, so you will work out. Agreed? Yeah, I mean, fairly straightforward, but some small algebra. So what's going to happen? This is going to move this way, right? Plus h nu q by 2, right? So it will move up by h nu q by 2. This will also go like this by same amount. But plus minus half, they move down by h nu q by 2. So this will go like this and this will go like this. Correct? So the central line, since both plus minus half shift the same amount, central line doesn't change, it remains h nu naught. The separation between the plus minus half remains h nu naught. But for this direction, for theta equal to 0, you now have see the three transitions possible, right? 3 half to half, minus 3 half to minus half, or half minus half. So this one is now larger by some amount. This is now smaller by some amount. So the line shape now is going to look a little different. Instead of a single line, so you will get, so you have a central line and then So I'm just drawing for a specific angle, okay, theta equal to 0. Where this is now, so this is frequency, intensity as a function of frequency. Right? So you have a central line and you have satellite lines. And in distance between the satellites is nu q for theta equal to 0.
So these two extra peaks are the satellite lines.
These two are called, this is called the central line because this arises from the plus minus half transition, and these other two are called satellite. So we are looking at spin 3 half, by the way. You'll have equivalent 5 half, a spin 1, you'll have similarly, you can work out what it is. So these two are called satellite lines, quadrupolar satellite lines. And this one arises from, so this is a higher frequency, so this is from the minus 3 half, minus half transition, and this is from the plus 3 half, plus half transition. Okay, watch out, this depends on the angle. So
then in principle, like while measuring these transitions, can one calibrate with respect to like which is the my theta equal to 0 direction? Only at that direction we will get.
yeah, so one should do, you should have a single crystal, and one should do as a function of angle how the position changes.
Right.
Yeah.
Then we can also find out like which is the principal axis for the
Right.
quadrupolar moment also.
That's right. That's right. You could do a pure quadrupole experiment. So a lot of things. Yeah. So this was, remember, for theta equal to 0, and of course we have taken theta equal to 0. No asymmetry. Otherwise, even the central line there's a shape change. So that we'll see a bit later. Okay. But this was theta equal to 0. Now often we are dealing with a not single crystal but a polycrystal powder. So you have randomly oriented crystallites, so all angles possible. Okay, so in any case, so you can also find out for what is the other case, right? So theta equal to pi by 2. So you can just evaluate this for the, keep theta equal to 0, but keep also cos theta equal to 0. Okay, so very easy to do same thing, right? Cos theta equal to 0, this is gone, this is anyway gone, so minus 1 from here, and then you just evaluate what this is. So, so it changes in the following way. It's actually higher. So whatever was, the minus 3 or minus half was now had greater separation. As you change the angle, suppose you could continuously change, this will now change and it will actually become smaller but by a different amount. So you'll work it out. So so it will be, maybe I should use different color.
So it could be sort of like a broad maximum.
Oh, yeah, but the weight associated with different angles is different because there's a solid angle, so sin theta d theta. That's the next thing we want to write down. So it is not just simple broad like this. There's different weight associated, so more complicated. So the satellite position, I mean, don't take the intensities too seriously. So what was here will actually move here. It will move the other side. Energy level difference was large. As you change the angle, it reduces and actually crosses on the other side, and this from here, this is another nu q by 2. And likewise for this one, it will come on this side. So, and again, so this will be at nu q.
The energy levels get inverted.
Inverted, yeah. So, question is, suppose you don't have a single crystal. Often we are dealing with polycrystals. Then you have all angles allowed, random orientation. What is the weight associated with each? And that will determine what the so-called powder pattern is. Okay, so for that, so one says that the intensity at a given frequency within nu and nu plus d nu depends on the angle like sine theta d theta. Okay, and therefore, so this is of course minus d cos theta. So this weight associated at each frequency goes as 1 over d nu d cos theta.
What is P exactly?
The probability, you can think of the probability, so the weight associated, what's the probability of finding a crystal between nu and nu plus d nu? That depends on the angle in this manner. So you have frequency as a function of angle. We have our expression. Okay, and so you just need to, so wherever d nu d by d cos theta becomes 0, small, you'll get a large contribution. Okay, so around theta equal to 0, it goes through maximum, and similarly, you can work out. You have, so for example, for spin 3/2 eta equal to 0, nu equals nu naught plus nu cube by 2 3 cos square theta minus 1, right? This is for eta equal to 0 and nuclear spin equals 3. Okay, so I can find out d nu d cos theta. Okay, and then I can check what the weight is. So again, I'll share these, but right now I just tell you what it is. So one can find out d nu d cos theta, and then if you write, what did I define as x? Yeah, if you call 2x plus 1 by 3 as cos square theta, you define x like that, then px, so the weight associated at a given angle, but in terms of x now, is 1 over root 3, 1 over root 2x plus 1, and x goes from minus half to 1. Okay, so if you now actually plot this, I'm plotting for one of the lines. So this there's a divergence here, and so if this is nu cube by 2, then this is nu cube, and so this is theta equal to 0, and this is theta equal to 90 degree. Okay, this is my central line position, this is nu naught, and you are looking at what the two satellite peaks will do. So here I am looking at the so-called left satellite, so one which decreased by energy for a particular angle. So as a function of the angle, of course it changes position, but also the weight changes. So this here goes by the name of singularity. Okay, and this is called a step. So there's a sharp change here, but here there's a singularity. You can sort of think of it this way, theta equal to 0 is only one orientation possible. Okay, so the weight associated, you need to have the crystallite really aligned like that. But theta equal to 90 is, any other crystallographic angles, right? Only between z applied field direction or VZZ and your crystal, if that is 90, then there are many orientations possible with 90. Okay, but with 0 there is only really one unique orientation. So of course with 90 you have greater weight. Okay, so this is what the weight of various angles is, and so finally, as you said, there's a overall broadening. So what you get is, something like this, and then you also have the other one. So right, so plus minus, so plus 3/2 plus half transition, also minus 3/2 minus half transition, and on top of that, of course, the central line. Okay, so overall line shape, if you could capture everything nicely, is right. So if you could capture everything nicely, so you'll have a step. So some broadening here, and let's see. So this is from one of the satellites, but depends on the angle. And remember, this is, let's say, my central line, and the other one will be here. So you get like this. Something like this, right? So it should be something like this, and the intensity is also, you should be able to write down. Transition matrix element, I think it's 3:4:3, if I remember right. Remember, we calculated the T1, where we said what is W1, 2, W2, 3, how are they related? Depends on the transition square of the transition matrix element. So if I remember right, this is the height is like 3:4:3 for these. So often it's not very easy to see these steps. You're doing a powder one, so there's overall broadening like this, and maybe not be CG. These are of course 1C. And so if you could just measure this, then this distance here in frequency is what is mu q, the quadrupolar frequency.
सर शी वाज टेलिंग कि हम लोग मेजरमेंट के वक्त कोई इंस्ट्रूमेंट यूज मतलब सॉफ्टवेयर यूज करते हैं सिमुल टाइप का टू फिट इट डायरेक्ट हम लोग उस पे सेंटर रख के अगर
हाँ, so there is a, so you can of course simulate these line shapes. You have the formula, what is the weight and what the spin and what the ratio, intensities, because what the transition matrix element. So one could write a program to that. There's this simul, Dresden, Max Planck, some guy wrote it. So what you can do there, you can input the value of the spin and value of the
nuclear we have to give, and then
nucleus you have to give,
which are allowed transitions that we have to click.
And whether you want to fix the ratio of the heights, you can do that.
We can do that using the various mu, q, eta. And
yeah, you can fix eta. So you don't sort of do a fit, you simulate what is the line shape for spin equal to 3/2, if the nu naught is so much, eta equal to 0, then what is it? And nu q is something. Then you put on top of it your own measured spectra, and then try to play with the eta and nu q, etc. So then the two match, and then you say, okay, then that's the nu q. But just visually, if you could have a line shape like this, then this is nu q. And you don't see any asymmetry, then eta is 0, close to 0. So yeah, so this is the first spin 3/2. What is the line shape? With eta equal to 0. A powder pattern with eta equal to 0. If eta is equal to if eta is not equal to 0, then you can imagine shapes are more complicated, because you see you had another term present, no? So we removed eta, right? So there was this eta cos 2 psi cos square theta, when that eta term was present. So that's going to cause trouble. I mean, no trouble, but it's going to make the line shapes asymmetric. So you will, even the central line you will not have symmetric like this. You will have some asymmetry to it. The satellites will also not be, even if you could do pure particular angle, it's going to have some shape to it because there's another variation there inside. Okay. So with asymmetry, you're not going to have nice pattern like this. You will have, I mean, you can look in literature, it's noted that single crystals people could measure nicely. So even central line can have a shape, and satellite also will not be like this. It will be something like this. You know, it's obviously more complicated.
Sir, what is the typical magnitude of the quadrupolar frequency?
Yeah, so it varies from, so depends on what the quadrupole moment is and depends on what the EFG is. So it varies from nucleus to nucleus. So strong ones like 63 or 65 copper, tens of megahertz. Typical in lot of oxide materials. Of course, depends on the environment, but of the order of tens of megahertz. So tens of megahertz you can nicely measure. There are some where, so Monica measured one, some cesium one, which was
10 mega.
really,
No, kilohertz.
Kilohertz. It was really small. So you could not see very nicely the satellites also. So with Simul you tried to put, and you could sort of make out there's some glitches there probably. So it just encompassed in the main line, central line.
Yeah, actually that's what I wanted to ask.
Yes.
What should be the sort of the frequency resolution in general?
Correct,
If
correct.
the nu q is very small,
Correct.
it will merge with this.
Correct. So typical line widths for the central line are easily tens or 100 kilohertz. So if your nu q is also of that order, you're not going to be able to resolve. And then to do a pure NQR experiment also not easy. You cannot really do NQR at tens of kilohertz. Your signal to noise is very poor. So good situation is where it's tens of megahertz. Then it is well separated from your central line. So lithium, for example, the one you are measuring now, this BRC sample, so the calcium or calcium equivalent had like 1 megahertz nu q. So then you can see it in even Fourier transform because you almost irradiate everything. So central line, and then that width is small, and you can see the satellite. Yeah. So you need to have megahertz or more to be able to resolve. So this is, remember, first order. If you now go to second order in perturbation theory, suppose the strength is larger than we said just now, then you have to consider second order effects. So no point in I just write the final answer.
Sir, if someone is doing this NQR,
Yes.
at least they are removing this issue of magnetic field, because we always want this zero field data.
Yes.
So if NQR is possible, that's always better.
I mean, if your frequency is high enough that you can do measurements, yeah. It gives also some information, yeah. Yeah, if you, more complications, firstly from first order you can go to second order in perturbation theory, still keep eta equal to 0, okay. So I'll share this, you get a long expression, but main point is that, see, earlier we found the central line was not split, half minus half, it's one transition really. There's no structure to it, it just goes like this, no structure to the central line. But if you consider in second order, then there is a structure to the central line also. So you'll get peaks at, so same, half minus half transition, right? So you have half minus half transition, you will get some structure to it. So you get mu naught 1 plus k. So this is just because of the Zeeman and then plus a night shift if you're thinking of a metal, and then the quadrupolar part. So for the central line transition, remember for first order there is no, it's still the same, right? In first order there's no change in separation of the plus minus half central line. But in second order, you have a second order term, so which looks like nu q square by 16 nu naught I times I plus 1 minus 3 4. Okay, but there is another feature, same plus minus half transition, where you have second feature is at, so peak, second peak, both from the same plus minus half transition, nu naught 1 plus k, and next one is minus nu q square by 9 nu naught, and then the same thing in the brackets here, I plus 1 minus 4.
That's symmetric.
Yeah. So in second order, even for eta equal to 0, even the central line is straight. Okay, so so you can calculate how much the splitting is, this minus this. So to find out k, what you would normally do is just central line position, and that tells you how that is shifted with respect to your nu naught. It will tell you what the night shift is. But if you have second order quadrupole effects, then what if there is no single peak? No, even central line. Even central line is, intensities are maybe not correct, but even central line is like this. So how do I get k? Well, then I have to work through this and then obtain. So one point is also that when you are dealing with second order effects, as you go to higher fields, nu naught increases, nu q doesn't change, right? It's a quadrupole related to the structure. Nu naught increases, so this prefactor decreases. So if you think of this as a width of the central line, as you go to higher field, they come close. So that's also a check whether it's this broadening or this double peak is effect of second order quadrupole. If you can do at different fields, if you find that at higher fields actually reduces, because otherwise magnetic broadening, all those things actually increase with field. The second order quadrupole decreases with field. So if you find a decrease, if you can see nice features, of course well and good, and then if you find that the distance decreases as you increase the field, then it's a clear indication of second order effect. And of course, once you find out what this distance is, and one minus the other, you can find out eventually, value of this prefactor and therefore then k. Okay, final objective is often to find out the night shift that's related to the spin susceptibility. Right, so this was just for eta equal to 0. If eta not equal to 0, then you get further structure beyond each of those lines. Okay, now the last thing is, forget quadrupole. Even in the absence of quadrupole, you're dealing with just single resonance, so spin half. Okay, so there's no quadrupole moment, so there's no issue. You can still get asymmetry of the hyperfine coupling, and so you can have kx, ky, kz different because the A hyperfine coupling is different along different directions, or maybe susceptibility is different. So then the shape is also not simple Gaussian, Lorentzian type uniform symmetric. It's going to be asymmetric. And there, so again, there's a convention. So one scheme is you note what are kx, ky, kz. The other scheme is when you call k iso as average of kx, ky, kz. And then you rather than talking in terms of kx, ky, kz, you talk about the isotropic part, the axial part, and then isotropic part. So the k axial is 1/6 2kz minus kx minus ky, and then the anisotropic part, just like the eta thing, it's half ky minus kx.
So that is kx plus ky plus kz.
Sorry, plus kz. Okay, so these are just alternate schemes. You can think of the night shift in terms of this diagonal components, kx, ky, kz, or often people quote these three are the k iso, kx, and k
So
aniso.
इस समय spectra, how will it look
Yeah.
like?
So once again, so one can, so nu is, so one can write in terms of the angle, some reference frequency, and then of course you have a night shift, so 1 plus k iso plus kx times 3 cos square theta minus 1 plus k aniso times 1 minus cos square theta cos 2 psi. Okay. So this is how the frequency varies with angle. Again, you have to provide for different weights for different angles. You can consider like before, p nu d nu is minus d cos theta, and wherever so your weight is proportional to 1 over d nu d cos theta. So you can find that out, and then once again so wherever d nu by d cos theta goes to 0, you get a large contribution, and the shape, I mean, we have already drawn it, but that was for a different thing. So if this is k iso, then this will be k perpendicular, k parallel, and so you'll get general broadening. So this is actually a singularity here, and then there's a step here. So this is spin half, let's say. Therefore, no quadrupole. It's just the anisotropy of the night shift, which is giving this shape. Okay. So different weights associated with different angles, and finally you get some overall broadening and something like this. Okay.
So if both the effects are present, then how do we distinguish? Because I mean,
Yeah. So of course, yeah, one second. This is for k and iso equal to 0, let's say. Yeah. So often you might have both present. Yeah. So already even with the quadrupole spectrum, we'll see the central line shape is not. So that central line shape variation, is it because of second order quadrupole, or is it because of this? At least if you could do with field, then if it increases with field, then it is not because of second order quadrupole. So yeah,
that's the only distinguishing feature.
that's the distinguishing feature. Correct.
Correct.
So that can be actually quite important. Yeah.
So in this case, our central, like the x-axis is our frequency, and this is the intensity. What the central line?
No. So you want to know? There's no. So you have. Let's say this is spin half.
Yeah.
Okay.
So central frequency.
Outer pattern.
Yes, and what is the central line? Which frequency we should pick up? That one or?
So no, k iso. You have to find k iso.
Okay.
See, you either talk about kx, ky, kz, or k iso will scale with the susceptibility 1/3 chi parallel plus 2 chi
Okay,
perpendicular. Okay. So k iso is here now in our notation, because anisotropy is 0, so I put kx equal to ky, no anisotropy, xy anisotropy. So k iso is just 1/3 of k parallel plus twice k perpendicular, and likewise you can write the k axial, right? K axial is 1/3 of k parallel minus k perpendicular. Okay, so the shape that you measure is like this. Your objective is to find out k iso. So one can, if one can pick out the k perpendicular and k parallel, then one can from this find out k iso. Or again, the simul software. So one can again generate the line shape as a function of angle using simulate based on the weight 1 over d nu d cos theta. That's the weight associated with each angle, and then one can obtain a simulate a pattern like this and match with your experimental pattern, find out k iso. Or if you can see these two step and singularities nicely, then you have figured out what are k perpendicular and parallel, and of course from that you can find out what is k iso. So objective is then to find out K iso.
Hmm.
And then plot that as a function of the isotropic susceptibility. So 1/3 chi parallel plus 2 chi perpendicular. And then we'll get the A, hyperfine coupling.
So second order perturbation where when central line splits.
Yes.
So that splitting with the field should decrease or increase, or it should remain fixed?
That's what I said now. The central line splits in second order. Since the second order term goes as 1 over nu naught. So as you increase the field, nu naught increases, so it should come closer. Okay, now if you have anisotropy also, then shape is so you will get, so there's the axial part also, no? So you get, draw another. So you get so this is when K iso is not equal to 0. So I get K naught minus Kx minus Ki iso, or this corresponds to theta equal to 90 degree and psi equal to 90 degree. And K iso is actually somewhere here. And you get this divergence at K naught minus K iso, Kx plus Kn iso. And this corresponds to theta equal to 90 and psi equal to 0. And then you get K parallel of course, is only unique orientation. This is equal to K naught plus 2Kx. And this of course for theta equal to 0. So this is, so just central line, I mean, it just says spin half, no quadrupole, just Zeeman, but there's anisotropy. So you should see a line shape like this, and then peak position is not the isotrope, K iso.
Mm-hmm.
Okay, you have to figure it out, I mean, by fitting, or if you can pick up these easily, then by combination you can figure out the Kx, K iso. Okay. Or you simulate, formula is known, so you simulate and then try to match it with the experimental pattern and vary by hand these parameters, so K and iso, Kx, and then see which way you can match the two, and that tells you what the parameters are. Right, so in general there are so many variations possible. You can have just Zeeman with no and Zeeman and isotropic. Okay. Simplest case, so from the peak position you get the frequency shift, you can work out everything. You can have Zeeman plus quadrupole, still let's say isotropic in that sense, in the sense of the central line. But you can have quadrupole first order, then the central line remains unchanged, and then the satellite positions depend on the angle.
Hmm.
If you have a polycrystal, then you'll get a powder pattern, and you can work out. You can have a stronger quadrupole, then you have to consider second order effects also. Still perturbation, so we see that then the central line also splits, but in a manner that the distance between those two anomalies decreases as you increase the field.
Mm-hmm.
Okay. On top of it, so here you can have eta not equal to 0, here you can have K and iso not equal to 0, you can have a combination of all that, so overall it can look quite messy. If you have higher spin 7.5 or something, it will be a nightmare. Right, so
in the cesium case we have 7/2.
you have 7/2, that is one thing, and the nu q is small,
Nu q
really
is
small,
small.
so it's all encompassed
Yeah,
and just enveloped within the single line. Yeah, so this also I have scanned already, so I can
So
share
one
this.
more thing.
Yeah.
In our sample, if we have two phosphorus,
Yeah.
then we get the two spectra line like T1
Yeah.
and T2.
So if you have
And-
inequivalent sites, they are seeing inequivalent magnetic environments. Then again, two. Yeah.
But then we like to know about the dynamic of this our system, we do 1 by T1 measurement.
Yes.
So why we have to do both of them? We can
Yeah.
take one and
Yeah.
tell about whole the system.
Yeah, yeah,
So many
yeah.
people
Unless one is because of some symmetry, one is missing out some fluctuations. Otherwise, anyone. Yeah.
but
In fact, if you have multiple nuclei, then again only one nuclei is enough.
yeah. But the physics is same.
Physics
Like,
is same. Yeah.
you do one, you do four.
Yeah.
It will be ten-
Unless because of the form factor of the hyperfine coupling, you are missing out. Something is getting filtered at some site.
Ah,
Then you will miss something, and then other one you will not miss. So other than that, yeah. No point in doing just multiple nuclei just for the heck of it. Yeah. Some may have a stronger hyperfine coupling, so you have better resolution.
Huh.
So all those things are true. Okay. So yeah. Anything else? I don't know. Right now we have samples where with the lithium you have sort of measurable new. Usually lithium also quadrupole moment is not. We have done a lot of lithium. Quadrupole moment is not very high. And
Scandium here उसमें
scandium, you saw the satellites.
yeah, that is like asymmetric. So one is little taller.
So whether it is this, the center line itself is
Central line